Um, Exam 4 is Monday. That is the 20th. 22nd. I just like to say 420. And the topics are everything up through linkages. Quiet you. Um, Anybody have any questions about the test? One homework problem?
No, will it just be one?
Oh, I think I'm going to probably break it up into pieces so that it's at least 2 or 3 problems. Make you tell me what the constraint equations are for something, or that kind of thing. Draw free body diagrams, but could be one. I like one problem tests, like aesthetically, I like the idea of it, but I think practically it's sort of better to be able to put a couple of topics on stuff. Okay. So now we're going back to, well, does anyone have any homework questions related to the test? Otherwise, we're going back to rotating coordinate system stuff that won't be on the test. Okay. So we're going back to particle kinematics. And by the way, since we're doing particle kinematics and rotating coordinate systems, really I'm calling this kinematics because that's the focus of this. But really, the only reason that you have to use this rotating coordinate system stuff is to express your kinematics in an inertial coordinate system. And the only reason you need an inertial coordinate system is to do kinetics. So it's kind of like we could easily combine this with Newton's second law and stuff to figure out forces. And last time I mentioned this, the big result. Everything in this section can be derived from this one equation. And this one equation, you can think of it 2 different ways, but these are both equivalent. It says for any vector u, the time derivative of u is equal to the way we're used to taking time derivatives of vectors, just the time derivatives of the components. But now, because of the issues caused by the rotating coordinate system, we have to add on correction term, which is capital Omega crossed with the u vector. That is the capital Omega is the angular velocity of the rotating coordinate system relative to an inertial coordinate system. Or equivalently, so this way here is useful for cases where your vector u is given as a function of time. The components are known as a function of time. That's not always the case. And then in the other cases, it's a little more helpful to think of it this way. The time derivative of u is equal to the observed time derivative of u. That's what someone who lived in that rotating coordinate system would think is the time derivative of u plus capital omega cross u. So this is like what an observer in the rotating coordinate system would see for u dot. That's the idea. And what they would see is the time derivatives of the components, you know, if they didn't know this thing was rotating. So now intuitively, why does that work? It looks like such a simple correction term, and it's not real clear why that correction term of capital omega crossed with the vector gives you that all that messy stuff, which was like ux times I dot plus uy times j dot. Remember, that was the stuff that caused us the problems. The stuff with the time derivatives of the coordinate axes. So what we're really asking is, why does capital omega crossed with u equal ux times I dot plus uy times j dot plus uz times k dot? You can reason it out in 3D the same way I'm going to do it in 2D, but it's just a lot more tedious and stuff. I think this, to me at least, is enough to sort of see where it's coming from. So this is enough for me. So in the 2D case, and 3D works similarly. Imagine your rotating coordinate system going from this coordinate system so there's your I, there's your J, your K is coming out of the board. So counterclockwise rotations here you can think of as rotations about the z-axis. And let's say that goes to, and it looks like it's a finite change in angle, just so we can see it. But the idea is that this is an infinitesimal change in angle where this, okay, so this is our x-axis at time t. This is our j-axis at time t. Over here, this is our I-axis at time t plus dt. This is our j-axis at time t plus dt. Since the rotation has happened about the z-axis is the same in both of those. And so we're going to use these to just sort of, the math is going to be like, I'm going to do the ugliest job. Like I did this once for the math department, and they were just like, oh my god, my eyes, they're like pouring acid into their ears and stuff. But the math works if you clean up some things. I'm just doing a really short thing that I think gives you the idea without all the stuff that you need to make it careful. But okay, so let's say here's our starting coordinate system. And a time dt later, we've gotten to this coordinate system. So here's I at the time t plus dt. Here is j at the time t plus dt. Okay. In that time dt, we've gone through a rotation. This change in angle is infinitesimal, so you can think of that as d theta z, and this would be the same, d theta z. Okay. And then, so what's the change in the vector I? And what's the change in the vector j? Well, if you think of these as like coordinates, the vector di is going to be the vector going from here to the finish, right? So this little thing will be di. It would really be infinitesimal. And this little thing would be dj. So I'll make so this vector is di. This vector is dj. And we are trying to express the vector. We're trying to figure out what di dt and dj dt are in terms of these. So why are we trying to do that? Why do we care what di? I'm just trying to keep you sort of on track of like what the hell we're doing here. Why do we want these? Yes. Yeah, because those are the problem terms. That's what we're trying to come up with an expression for. Ux times I dot and blah, blah, blah. Okay. So di dt is equal to, you can think of it as let's take, sorry, Nancy. Let's first just figure out what di is, and then we'll use that to come up with di dt. Okay, so di is equal to the magnitude of di. And what direction is that in? Well, remember that this is an infinitesimal rotation, right? It's supposed to be. And so these are really the same direction, right? This is what they hate in the math. These are really the same direction because that angle is really infinitesimal. Okay? And so what's the direction of di? It's pointing that way. It's in the positive j direction. You see that? And so the next thing we have to figure out is what's the magnitude of di. And we can use trigonometry here to figure that out. these both have a length of 1. You see that? Um, these are unit vectors because they're coordinate system axes. So it's an isosceles triangle, but it's also a right triangle because that angle is infinitesimal. Okay. So DI is equal to, if you think of this as a right angle, equal to 1 times the sine of d theta z. And this they like in the math department. Um, now that that angle's infinitesimal, we're taking a limit as that goes to 0. What's the limit of sine d theta z as d theta z goes to 0? Well, that's true. But as a first order power series, the sine of that angle just goes to the angle in radians. Remember that? That's a really useful fact. So this is equal to d theta z. Okay, so both of these two together say that di is equal to d theta z times j. And now that we have that, we can say that di dt, divide both sides by the increment in time, is equal to d theta z dt times j. Okay. Well, d theta z dt, that's just the definition of the z component of the angular velocity of the coordinate system. And so we can just write this as capital omega in the z direction, the z component of the angular velocity times j. Well, and so this whole, what I mean is this is equal to capital omega z component times j. Yeah, of the coordinate system. Okay, so same idea for dj dt. But now if you think of these two axes as being in the same direction, because this angle is infinitesimal, what's the direction of dj? Negative, yep, exactly. Negative I. And so dj is in the negative I direction. And so if you go through those exact same steps again, you get that dj dt is equal to negative omega z times I. So what we're looking for, these correction terms that we're trying to come up with an expression for, are ux times di dt or I dot plus uy times j dot. And what we've figured out now is those are equal to ux times this thing, j, minus omega z times uy times I. Yes. Yeah, capital Omega is always going to be the angular velocity of a coordinate system. Lowercase omega is always going to be the angular velocity of an object. Okay, so omega is always angular velocity, but the capital always means we're talking about the coordinates. And I'll go through a little list of some things to try to keep straight with as these. Okay, so here's what we end up with. And this is 0, 0, omega z crossed with ux, uy, u. I guess we're doing this in 2D, so this would be 0. So we have negative omega z uy for the x component. That's this one. Positive omega z ux, and then 0 for z. Okay. So that's sort of if you ever are working through stuff and you think like, wait, why is like, it's such a simple result. It's so surprising. We have this weird derivative thing that just comes out to be a cross product, the angular velocity and the original vector that we have. Well, this is why. And it comes from the directions of the DI and DZ vectors that we get that cross product. Any questions about that? Yep. It would still work out because these are infinitesimal angles, and so multiplanar angles are really tedious to work with unless they're infinitesimal, because if you go, so say you start out by rotating around the z-axis, and now you rotate about the x-axis. That doesn't give you the same position as doing the x rotation first and then the z rotation. You know, it's just really a pain to deal with. But as long as those are infinitesimal and your rotation about z hasn't in any finite way changed the orientation, it makes it all easier to work with, and you can think about it this exact same way. Any other questions? If you never want to think about that again, or even if you didn't think about it this time, you never have to. But that's where it comes from. Okay, everything else in this section comes from applying the big result to different kinds of vectors. Well, what are the two vectors that we're going to, I mean, really, there's only two vectors that we want to take the time derivative of in a rotating coordinate system. Since we're dealing with, um, particle kinematics, we want to take time derivative of position to get the velocity, and we want to take the time derivative of velocity to get acceleration. So we mainly will just use this for the time derivative of the position is equal to the velocity, and the time derivative of the velocity is equal to the acceleration. Not, you know. Okay, so let's do that now. So first, we'll take the time derivative of the position. So try as much as you can to get your bearings with this stuff. If we have a position vector and we're trying to take the time derivative of it, is that a position vector in an inertial coordinate system or in our rotating coordinate system? Or is this a trick question? Yes? Any other answers? It's the same for both of them because we're always assuming that instantaneously, at whatever instant we're considering, those two are at the same orientation. At the next instant, they won't be at the same orientation, and a position vector doesn't have any derivatives in it, so we don't have any of the problems that come with rotating coordinate systems. You know, come up with something that the position is the derivative of. I dare you. You can't. You know? So the position is simple. The position in the rotating coordinate system is the same as it would be in the corresponding inertial coordinate system. The problems come about when you take the time derivatives. Okay. Yep. I love that question so much. Well, we are going to, you can think of, well, I guess I don't love it that much. Really, everything we do is a parameterization, because we're expressing the components of the vector as functions. So really, that's like we're never writing things as functions, and if we ever write them as functions, we just turn them into these vectors. You know, what I was thinking that was leading into is expressing things in polar coordinates, and we're going to do that pretty soon. Semi-related, but really, just think of it as like everything we do is a parameterization. Okay. A parameterization is just something where you have some parameter. In our case, it's almost always time, and you're representing all of the components of the vector as functions of that parameter. Okay, so, well, the velocity vector is just equal to the time derivative of the position. And so we're just applying the big result one time to the position vector. So it comes out looking just like the big result. You know, it comes out looking just like time derivative of the x component of position, time derivative of y component, time derivative of z component, plus angular velocity of the coordinate system crossed with the position vector. Or equivalently, you can write it as the velocity is equal to the observed velocity, what someone watching this motion from a camera that's rotating with the coordinate system thinks is the velocity. You know, like in the astronaut example, a camera that's rotating with the arm of that thing thinks that the astronaut's velocity is zero because all it sees is the astronaut at every instant, you know, and that would be the observed velocity in that rotating coordinate system, and then plus capital Omega crossed with. Okay, that one was easy. So that's the velocity. So now we're really feeling confident because that one was easy. But the problem is for the next one, calculating the acceleration, you know, the difficulty is that now we're going to apply the big result to this thing that's already gotten a little bit ugly. Now things are going to start to get sort of out of control. You know what I mean? So the acceleration, so apply the big result to this thing. Okay. And so the acceleration, all we're doing is taking the time derivative of the velocity. But we'll think of that as the time derivatives of the components plus omega crossed with the velocity vector. And when we take the time derivatives of the components, we're going to be taking the time derivatives of this whole thing, of the components of this whole thing. And when we take the cross product, we're going to take the cross product of this whole thing. Okay. So because it's going to get messy, I'm going to break it up into two pieces and then add them back together. So I'm going to do this first and then this second. So Vx, Vy, Vz components dotted. Is equal to, so let's go up to this first one. Okay. What do you get if you take the time derivative of the components of px dot, py dot, pz dot? This is really the easier one. We're just taking derivatives of the components. So now we're getting second derivatives of these. And now for the cross product of omega and p, we have to use the product rule. So we have plus capital Omega dot cross p plus omega crossed with time derivatives of the components of p. Let me say one thing. I never know like how much detail to go into this stuff, but I think there's so much subtlety to all of this, you know. And like one thing is, okay, we got this by taking the time derivatives of all these things, the components of all these things. But right here, I did like it looks like at first I did the most egregious thing. Instead of saying that I took the time derivatives of the components of this omega, I just said I took the time derivative of omega. That's the whole, so all of these problems come about because that is not equal to, the time derivative of the components is not equal to the time derivative of the vector. So why could I do this? Well, you can do that because to take the time derivative of a vector, it's equal to the time derivative of the components plus omega crossed with the vector. What's omega cross omega? 0. The cross product of any two parallel vectors, so any two equal vectors, is 0. And so this is just equal to the time derivatives of the components. I don't know. That might be going a little too far into the weeds, but this is the kind of stuff as you're going through it, you'll be like, oh, I totally understand this. And then just one night at 11:30, you'll be like, what? Okay, so we got that piece. And now we're just doing, so this was our piece 1. Now we're on to our piece 2. That's omega crossed with the velocity vector. And so that is omega crossed with, this is our velocity vector. So we're just taking the cross product of all these pieces. So omega cross with the time derivative of the components of position. And then the time derivative of, the cross product of omega with the quantity omega cross p. So this is just equal to omega cross quantity omega cross p. Yes, that is a very good observation, and I have a whole list of differences between the two to try to keep this stuff straight. Yeah, there's a lot of terms that look like the watermelon equation in here. Okay, so put them together, and you get your final answer for acceleration. That is, the acceleration is equal to, we have the second derivatives of the components of position plus omega dot cross p plus, notice we're adding 2 of these omega crossed with the time derivative of the position components. So 2 omega crossed with components dot plus omega cross quantity omega cross p. Or equivalently, the acceleration is equal to, what would you call this term? As far as like what somebody living in the rotating coordinate system would see. Yep, perfect. So that's the observed acceleration. plus omega dot crossed with P plus 2 times omega crossed with, this is the observed velocity, plus omega cross quantity omega cross P. So you get that messy equation, and I'm going to put, like on tests, I'll put this equation on there. You're not going to have to derive that, but I just want you to recognize that, you know, the equations we're going to use most are the formula for velocity and the formula for acceleration, but they all just come from what we figured out about time derivatives of general vectors. Okay. Um, um, so compare this acceleration equation to the watermelon equation. You know, they definitely look similar. So let's get straight what the things that look similar measure in each of the two cases. Um, so, well, let's just look at them for a second. So we have this one that we just did. Well, let me do the watermelon equation. So A is equal to alpha cross R plus omega cross quantity omega cross R. Versus what we just figured out is acceleration is the observed acceleration plus capital omega dot crossed with the position vector plus 2 times capital omega crossed with the observed velocity vector plus capital omega crossed with the quantity capital omega cross P. And the things that look similar are this and this. I mean, I could have written this as a capital alpha. You know, the time derivative of an angular velocity is an angular acceleration. So those look very similar. And then these two look very similar. So what you have to be really careful to keep straight on is basically like what the different omegas mean, what the R means, what the P means. Okay. Okay, so the first thing, lowercase omega versus capital omega. Lowercase omega is always an angular velocity of a body. Capital omega is an angular velocity of a coordinate system. Same thing with alpha versus capital omega dot. Alpha is an angular acceleration of a body. Capital omega dot is an angular acceleration of a coordinate system. Three is R versus P. R is a vector from the center of a circular or spherical motion to the desired point. P is a position vector, which means, if you put it out in words like this, P is a vector from the coordinate system origin to the desired point. So those are different. The center of the circular spherical motion doesn't have to be at the origin. Okay? If it is at the origin, then those are the same, but in general, they're not. And the last thing I want to say, well, let me say 3 more quick things. This thing, capital omega dot cross position, is an unobserved tangential acceleration. So that's part of like a correction term. Fifth, omega cross quantity, omega cross P, is an unobserved centripetal acceleration. And this leftover thing, 6, this sort of hodgepodge of things we've thrown together, 2 times capital omega with this observed velocity, called the Coriolis acceleration. Have you ever heard that term before? It's the reason in popular culture, people think of it as the reason that, mostly because of a Simpsons episode, that toilets flush the opposite direction in the southern hemisphere than they do in the northern hemisphere. There's something to that, but it doesn't really happen because it's a very small force. But it has some sort of recognizable things. I think of it as just sort of a hodgepodge, like you're throwing the rest of the stuff together. But it does have this name, the Coriolis acceleration. Apparently, there was someone named Coriolis who thought it was cool. Okay. Any questions about that? All right, that's all the background on this stuff. No more math about this. Now, the rest of the time, at least the next 2 classes, we're just going to do examples, figure out how to use this, that kind of stuff. All right, that's all.